This video is about complex number in polar system. First of all, let's look at this coordinate system. It's a complex number system. On the x-axis, we use real number. And on y-axis, we use imaginary number. So this coordinate system, we can express any complex numbers. We use a plus bi to stand for any complex number. And the absolute value of this complex number will be square root a squared plus b squared. In other words, the distance between origin and this complex number, then it's equals square root a squared plus b squared. And let's assume this angle is theta. So we know that a equals r times cosine theta. And b equals r times sine theta. So in polar system, we can express any complex number z equals r cosine theta plus I times r sine theta. Sometimes this form can be abbreviated as r cis theta, so that people know this is the distance to the origin, and a cosine and I sine, then this is a theta. Here is a conclusion: polar form of all complex numbers. The polar or trigonometric form of complex number we can express as this one, where theta is called the amplitude and r is called the modulus. This form sometimes is abbreviated as r cis theta. Therefore, the relationship between complex number and its polar form will be like this. R will be the square root a squared plus b squared for a plus bi. And this a equals r cosine theta and b equals r sine theta. For theta part, you have to be very careful. If a greater than 0, that means it's on the first quadrant or the fourth quadrant. Then we just take inverse tangent of b over a. That's it. But if it's on the second or third quadrant, you have to make sure that inverse tangent of b over a plus pi. This is very important. So you have to decide which quadrant for your complex number, so that you decide you add pi or not. Let's go to example 1. Express each complex number in polar form. Polar form will be r cis theta. So we need to figure out this r and theta. According to this given complex numbers, we know it's on the first quadrant. And r will be square root 4 squared plus 4 squared. So we got square root of 32 means 4 square root of 2. since it's on the first quadrant, so theta we can do inverse tangent of b over a. So 4 over 4. You get inverse tangent of 1 means pi over 4. Therefore, its polar form will be 4 square root of 2 cis pi over 4. So this is the solution. Now let's go to 11. For 11, which quadrant? It will be second quadrant. Therefore, your r equals -2 squared plus 1 squared equals the square root of 5. And theta equals inverse tangent of 1 over -2, then plus pi. If we put into a calculator, you will get 2.68. If we want to use degree, it will be 153.43 degree. Therefore, its polar form will be square root of 5 cosine 2.68 plus I sine 2.68. Or you can use degree doing square root of 5 cosine 153.43 degree plus I sine 153.43 degree. Let's go to example 2. Graph each complex number on a polar grid, then express it in rectangular form. For number 20, we know that r equals 1 and theta equals 11 pi over 6. Therefore, we first find the 11 pi over 6, then find r equals 1 will be here. These points. Then its rectangular form, we will work this out. For cosine 11 pi over 6 will be square root of 3 over 2 plus I times sine 11 pi over 6 will be -1 over 2. Therefore, rectangular form will be square root of 3 over 2 minus 1 over 2i. Now let's go to 21. First of all, we need to graph this complex number on this polar grid. From given information, we know that r equals 2 and theta equals 4 pi over 3. First of all, we will find out 4 pi over 3. It's here. Then get the r equals 2. It will be this point. And for the rectangular form, we work this out. We will got the 2 times. Cosine 4 pi over 3 is -1 over 2. For sine 4 pi over 3, it's a negative square root of 3 over 2. So we put I. Then we do distributive property. We got -1 minus square root of 3i. This is the rectangular form. Why do we use a polar system to show complex numbers? It's so easy to do the operation of a product, quotient, or in the future, we can take exponent of a complex number. If we use a polar form, it makes this operation so easy. Here is the formula for product part. When two complex numbers multiply each other, we just multiply the r together and you add this angle. If we do quotient of two complex numbers, then we just need to do the quotient of this r, and an angle will be the difference of those two angles, just like this. It's so easy to do. For example 3. Find each product or quotient expressed in rectangular form. For number 27, we multiply r together, so that will be 10. Then you will get cosine, add these two angles, 135 degree plus 45 degree. Then plus I sine 135 degree plus 45 degree. So we get 10. And for cosine, we got 180 degree. Then plus I sine 180 degree. So we work this out. You will get 10 times -1 plus I times 0. So our final answer will be 10. Now let's do 28. For 28, we do 3 divided by 1 over 2. Then we do for cosine 3 pi over 4 minus pi. Then plus I sine 3 pi over 4 minus pi. Work this out, we got 6 and a cosine negative pi over 4 plus I sine negative pi over 4. Now we use the rectangular form, will be 6. Cosine negative pi over 4 is the square root of 2 over 2 plus I negative square root of 2 over 2. So we got 3 square root of 2 minus 3 square root of 2i. Let's introduce the Moiras theorem. You can use method for finding the product of a complex number in polar form to arrive at the method for raising a complex number in polar form to a power. And the result is known as the Moiras Theorem, like this one. Or I can write down like this. Basically, you take n's power to this r, and then your angle multiplied by this n. Now let's go to example 4. Find each power and express it in rectangular form. According to the Moiras Theorem, we know that 4, we have to do 4th power. Then we get cosine. Pi over 2 times 4, it will be 2 pi plus I, then sine 2 pi. So we got 256 times 1 plus I times 0. So final answer will be 256. For 39, if you want to do square root of 3 minus I to the 3rd power, you have to do the FOIL like square root of 3 minus I times the square root of 3 minus I, square root of 3 minus I. Then you have to do the FOIL. That's a lot of work. So first of all, we need to change this into polar form. Polar form will be r c I s theta. So we need to figure out the r equals square root a squared plus b squared. We know that a equals square root of 3 and b equals -1. So we plug in, we got 3 plus 1 equals 2. And for theta, you have to decide this complex number in which quadrant. We know this will be on the 4th quadrant. Therefore, we will get inverse tangent of -1 over square root of 3. You don't have to add a pi. So we get -pi over 6. Therefore, for polar form of this complex number will be 2cis -pi over 6. Then this time we do the 3rd power. You will get equals 2 to the 3rd power. Then cis, here you get -pi over 2. Therefore, we got 8. Then we do cosine -pi over 2 plus I sine -pi over 2. So we work this out. We get 8 times 0 plus I times -1. Final answer will be -8i. In other words, -8i will be the solution to square root of 3 minus I to the 3rd power. Let's go to distinct roots of a formula for these complex numbers. For a positive integer p, the complex number in polar form RCIS theta has p distinct pth roots. They are found by this formula. So answer is not a unique one. You have to work out when n equals from 0 to p minus 1. For this formula, you have to do r to do the p's roots. And then you have theta divided by p, but remember to the numerator you have to add 2n pi. Because for sine and a cosine, the period is 2 pi. For example 5, find all the distinct piece roots of the complex number. First of all, for negative I, you have to change into polar form. So we know that A equals 0, B equals negative 1. R definitely equals 1. And for theta equals 3 pi over 2. Therefore, for the polar form for negative I will be cosine 3 pi over 2 plus I sine 3 pi over 2. Then I have to do 1 over 5th power. So we can get cosine 3 pi over 2. You have to add 2n pi, then divided by 5. We do the same thing for this sine. So we got 3 pi over 2, add 2n pi over 5. Then n equals 0, 1, 2, 3, 4. So let's organize these expressions. We got cosine and denominator it will be 10, and got 3 pi plus 4n pi. Plus I sine. Denominator is 10. Then 3 pi plus 4n pi. Now we will make n equals different integers from 0 to 4. Then we can work out 5 solutions to this problem. So when n equals 0, I will get the cosine 3 pi over 10 plus I sine 3 pi over 10. It's equals 0.59 plus 0.81i. We call this is Z1. When n equals 1, we got Z2 equals cosine 7 pi over 10 plus I sine 7 pi over 10. So we get negative 0.59 plus 0.81i. So when n equals 2, we got Z3 equals cosine 11 pi over 10 plus I sine 11 pi over 10. Negative 0.95 minus 0.31i. So when n equals 3 and Z4 equals, you could see the pattern. This is a 3, I go to 7, from 7 go to 11. That means basically I just add 4. Therefore, we got cosine 15 pi over 10 plus I sine 15 pi over 10. Reduce 15 pi over 10 will be 3 pi over 2. 3 pi over 2. Therefore, we can get, this is a 0, and for this part it's negative I. When n equals 4 and Z5 equals, I keep adding 4 pi to the numerator, we got cosine 19 pi over 10 plus I sine 19 pi over 10. Therefore, we got 0.95 minus 0.31i. Let's go to next question. First of all, we need to change this complex number into polar form. So we got r equals square root 4 square root of 3 square plus negative 4 square equals 8. For theta, you have to figure out which quadrant that complex number is located in. So we know this will be the fourth quadrant. Therefore, theta equals inverse tangent of negative 4 over 4 square root of 3. So you will get negative pi over 6. Therefore, for polar form, for this complex number will be 8 CIS negative pi over 6. Then we take fourth roots, so 1 over 4th power. Therefore, we got fourth root of 8 CIS negative pi over 6 plus 2n pi over 4. Then we simplify, we got fourth root of 8 CIS 12n pi minus pi over 24. Now we can set up when n equals 0, 1, 2, 3 separately, and we can figure out the solution to this problem. So all these 4 will be the solution to this problem.